Good day. My name is Giancarlo Sanchez, and I'm a software engineer. Today, I'll be exploring why unguided processes can't build Google or DNA through a thought experiment. We'll bridge biology and technology to highlight how randomness alone cannot account for the complex functional systems we see in life's ultimate software, DNA. Here's the big question. Is life the product of random chance, or does it point to a masterful design? Darwinian evolution attributes the origin of life to random mutations and natural selection, while intelligent design suggests that life's complexity and functionality require an intelligent cause. This presentation will demonstrate that randomness is insufficient to explain the complexity of DNA, pointing instead to intentionality and intelligence as the most plausible explanation. While this presentation welcomes everybody, it is particularly crafted for engineers, software developers, STEM students, and skeptics familiar with logical systems and technical processes. Let's dive in. Let's start with a simple analogy. DNA is often referred to as life's code because, like software, it stores, processes, and executes instructions. Each base pair in DNA can be likened to a line of code in a program. In both cases, these sequences must be precisely structured to function correctly. For example, a single error in your program can crash your application, just as a mutation in DNA can disrupt critical biological processes. This analogy lays the foundation for understanding the parallels between biology and technology. DNA and software systems like Google Maps share three characteristics: language, information, and execution. Google Maps operate in binary, zeros and ones, while DNA uses a four-letter code, A, T, G, and C, which are chemical bases. Google Maps stores vast amounts of geospatial data, while DNA holds the instructions for building and maintaining life. And Google Maps code runs on hardware. For DNA, cellular machinery reads the genetic code and builds proteins, the building blocks of life. DNA and Google Maps also share traits that highlight intentional design. Resilience. Google Maps adjusts recommended routes based on road closures, while DNA has built-in proofreading mechanisms to fix errors during replication. Google Maps helps users navigate, while DNA produces proteins like insulin, which are essential for life. And they are both modulars. Engineers don't reinvent the wheel. Google Maps reuses libraries for efficiency, such as the one that handles date formatting, just as DNA reuses genes across different organisms, like one handling cell replication in a banana or a human. Another set of parallels reveals the sophistication of both systems. They're both hackable. Through Google Maps, just as Google Maps can be modified by a developer, DNA can be edited through genetic engineering. But modifying either system requires understanding its design. They both are backed up. Google Maps uses redundant servers to prevent data loss, while DNA stores spare chromosomes as backup mechanisms. They're both optimized. Google Maps compresses data for efficiency, and DNA fits billions of base pairs into microscopic chromosomes. Richard Dawkins, a renowned biologist, evolutionary biologist, and leader of the new atheist movement, says that DNA is a digital code, the program of life written in a four-letter alphabet. David Baltimore, a biologist, says that modern biology is becoming a branch of information technology. The sequences of DNA are instructions, like a code for a computer program. Craig Venter, lead Human Genome Project geneticist, says that life is a DNA software system. And Bill Gates, co-founder of Microsoft, says that DNA is like a computer program, but far more advanced than any software ever created. Some may argue that comparing DNA to software is misleading because biological systems evolve and adapt, while software is static and designed. However, The analogy between DNA and software is not about their ability to evolve, but about their shared reliance on coded information. DNA stores, processes, and execute instructions in a way that is fundamentally similar to computer programs. Both systems require precise arrangement to function. Furthermore, DNA shows signs of optimization, like for example, error correction or redundancy, which is characteristic of intelligent systems and not random processes. These optimizations indicate intentional design rather than blind evolution. Optimization involves improving a system based on specific criteria, like efficiency, functionality, or precision. Without a purpose, there are no criteria to guide or measure improvement. So random processes may produce changes, but these changes are not inherently directed toward a beneficial or functional outcome. Let's take a closer look at the analogy. Each base pair in DNA is equivalent to a line of code. For software to work, every line must fit into a coherent program. Similarly, DNA sequences must align perfectly to produce functional proteins. However, it would be safe to assume that DNA and software code is a valid analogy. To appreciate the complexity of DNA, let's compare it to software. Pacman has about 1,000 lines of code. An E. coli bacteria's DNA has 4 million base pairs on its DNA. All Google services, one of the most complex human software ecosystems, has 2 billion lines of code, and human DNA, a staggering 3.3 billion base pairs. So here's our hypothesis. If an unguided process cannot create a working software program, then an unguided process cannot explain the precise design of DNA for life. Some people may argue that natural selection is not random. It's a guiding process that can create complexity over time. However, while natural selection is not random, it relies on random mutations to generate the raw material for evolution. The problem lies in the ability of these random mutations to produce the level of specified complexity and functional information seen in DNA. For natural selection to act, there must be a population of replicating entities with variations to select from. However, the machinery required for replication, like the ones seen in proteins, enzymes, RNA, or DNA, is itself complex and unlikely to arise by chance. This creates a chicken and an egg problem. The replication machinery depends on pre existing information encoded in DNA or RNA, but that information cannot arise or be maintained without replication. But what about chemical evolution? Chemical evolution cannot account for information. The prebiotic environment, or before life began, would have been dominated by random chemical interactions. While chemistry can explain the formation of basic molecules like amino acids or nucleotides, it cannot explain the organization of these molecules into information bearing sequences such as DNA or RNA. Without a guiding mechanism, random chemical processes are extremely unlikely to produce the specified sequences required for functional self replicating systems. Dr. William Dembski is a mathematician, philosopher, and pioneer in intelligent design theory. He is known for developing the explanatory filter and publishing extensively on design detection and specified complexity. He developed the explanatory filter to explain the origin of things. Three categories reflect the major modes of causation recognized in science and philosophy: deterministic processes or natural laws, randomness or chance, and intentionality or design. No phenomena currently require a fourth category. The filter has been successfully applied to distinguish between natural and artificial causes in fields like archaeology, identifying natural formations from man made artifacts, for example, and cryptography, detecting intentional patterns. Critics, especially from the evolutionary biology community, argue that natural selection combines chance and law, making design unnecessary. However, the explanatory filter remains robust because all known causes of phenomena can be classified into natural law, chance, or design, Proposed alternatives either fit within these categories or fail to provide a distinct explanatory mechanism. As such, the filter is comprehensive for evaluating the origin of complex specified systems like DNA. Emile Borel's limit of chance in our finite universe is 10 to the minus 50. Emile Borel was a renowned French mathematician and probabilist who pioneered modern probability theory. His work on measure theory and thresholds for impractical impossibility remain foundational in science and mathematics. He proposed a threshold for practical impossibility, this number 10 to the minus 50. He said that events with probabilities below this threshold are so unlikely that they effectively cannot occur within the physical universe. Events with probabilities lower than this threshold cannot happen within the finite universe. For example, getting struck by lightning is 10 to the minus 6, which is equivalent to 1 in a million. Winning a lottery by guessing a 6-number draw is 10 to the minus 7, which is equivalent to 1 in 10 million. Or solving a Rubik's Cube by randomly moving faces is 10 to the minus 19. While highly improbable, these events can happen. They can happen. However, others, such as finding a particular grain of sand on Earth, or brute forcing a 256 security key encryption, or generating all the information bearing infrastructure in the precise sequence to generate an E. coli bacteria 4 million base pairs DNA, are mathematically impossible, even if all the particles in the universe since the beginning of time were involved in the process. There is just not enough possible events for them to happen. For the bacteria, it involves building amino acids that build into proteins that are encoded into DNA that form the genome. There is an exponential complexity that we will illustrate in the next slide. But why consider this threshold? Borel's threshold is widely respected in probability theory because it contextualizes probabilities beyond human intuition. It establishes a practical guideline for distinguishing between improbable but possible events and events that exceed the scope of physical reality. Emile Borel's threshold is a scientifically valid tool for distinguishing possible events from those that exceed the universe capabilities. If events below 10 to the minus 50 are deemed practically impossible, then the chance-based origin of DNA, which its probability exceeds the limit, strongly supports the need for a guiding intelligence. This guiding chart illustrates two lines for both complexity in blue and improbability in red. Along the Borel's threshold, a green dashed line on top for practical impossibility. Our x-axis, or stages of DNA formation, tracks the progression from amino acid formation to the full E. coli genome. So going from amino acid formation to protein formation, DNA encoding, and finally the genome. Our y-axis refers to complexity. It represents the increasing complexity of each stage, with higher values indicating more intricate structures. And our right vertical axis shows the decreasing likelihood of achieving each stage through random processes. The lower the value, the less probable. So anything below the green dashed line is in the domain of practical impossibility. Mathematically speaking, only the generation of amino acids from unguided processes is possible. Building a protein from 150 amino acids, a 150 amino acid protein requires 450 nucleotides. All are these below threshold of mathematical possibility, meaning that they're mathematically impossible. Some people may argue that the improbability arguments are flawed because highly improbable events happen all the time. However, while improbable events can occur, the key distinction is between plausible improbabilities, like example winning the lottery, and practical impossibility, generating functional DNA through random processes. Let's put randomness to the test. Here's a simple Python program. Print welcome to the matrix. It has 26 characters chosen from an ASCII set of 188 possible symbols. 128 possible symbols. The probability of randomly generating this code is 10 to the minus 52, already beyond Borel's threshold. Now imagine trying to randomly generate Google's 2 billion lines of code, let alone the 3 billion base pairs in DNA. It's clear that randomness cannot produce such complexity. This is a sample program that randomly tries to generate our program print welcome to the matrix from before by changing characters on a string. If we let this random typing program run forever, it still would not generate our basic application, much less a functional code base like Google Maps or DNA. Random processes don't create order or functionality, they produce chaos. And this visual emphasizes the futility of attributing DNS complexity to randomness. If we let this application run, it will never finish. So we just stop the video now. So we can conclude that DNA works like a computer software. It stores, processes, and executes precise instructions. Randomness cannot create software. Even small programs are impossible to generate through random typing. Randomness can't create DNA. The complexity and functionality of DNA requires intentional design. If software like if software systems like Google Maps demand engineers, why wouldn't DNA, which is far more advanced, require a designer? Thank you for your attention. If you'd like to learn more or join us in the conversation, visit the Apologetic Network, and let's continue exploring the evidence for design in nature and engage with others in meaningful discussions. Feel free to scan this QR code to connect with me and access additional resources in the network. Thank you.